right. So as advertised, the last couple of weeks, 4 weeks now left, about 6 lessons, so 6 lectures. We are going to alternate between material from basic quantum mechanics and quantum computing. And as you'll see, it's amusingly feasible to go through topics that make minimal use of basic quantum mechanics. As you'll see now in the Grover search, it'll essentially be a qubit rotation problem in disguise. In other words, it's a two-state solution. Okay, can you see my screen? Just to make sure, I guess I can share and share it again. Well, just to make sure I'm not confusing everybody. Can you put in the chat if you see my screen or not? My slides, that is. It should say Grover search 5.4, which is today's date.
Yes, I can see it.
Yeah.
Yes.
Okay. Are you awake?
Yeah, I'm up.
I hear some sounds. Okay, at least one person is attempting to answer. Ricardo, I think that's you. All right, I'll take what I can get. Let's just keep going. So what is search? So usually, I think we're generally used to somewhat structured searches, right? That's why we'll have alphabet. That's why we have the numerical system. If you have a number, usually the way you'll store it will be in some structure, in some hierarchy that allows us to search things smartly, okay? But you should appreciate that alone is a consequence of somebody else's work. Somebody had to invent the alphabet, somebody organized the information, and so on and so forth. You know, and some information is generated by human activity, so it's naturally organized. But there are also examples where information is just a bag of information. There's no rhyme or reason. You go out and you collect. There's actually an interesting, just came to mind, an interesting example from archaeology I remember learning about when I was a grad student, when they were excavating La Brea tar pits. So it's a big sort of a you know, area with lots of tar and lots of bones of, you know, prehistoric animals. They were in a hurry because there was some construction. This is in Los Angeles, right? So there was some construction, so they excavated a bunch of it, and then they thought, hey, let's just dump it in a solvent. The solvent will melt out the tar. And of course, when that happens, all the bones it's just a big bag of bones. And so the Natural History Museum in Los Angeles still has that big bag of bones that they put summer students or summer interns to try to sort out, like little chunks of it. Because, you know, the relative location and space of the bones is really important. And so nowadays, I mean, or the correct way to do archaeology is to, you know, piece things together. It's like a crime scene, right? Anyway, this is just an example of how much of a difference there is between a structured and unstructured search. The subject of today's lecture is unstructured search, and unstructured search means you keep checking, you know, there's an entry in the database that you're looking for, and if you're searching for it, you know, say the little bones and you know, of saber-toothed tigers and whatnot, you're gonna like pick it up and say, oh, is that you know, is that the third rib? No, it's not the third rib, and so on and so forth. So if you got a big bag of size N, you know, worst case scenario, you have to look through every single one to decide whether the thing is even in the bag. you might get lucky, so you'll go through half of them and you might statistically get something, but it's basically a difficulty of order n, the size of the database. And the reason we're having a lecture today is because not too long ago, I think maybe in the 80s, I want to say, I should check that. Love Grover is a computer scientist who knew a little bit of quantum mechanics. He realized that using quantum mechanics, one can perform unstructured search in square root of n steps. Again, here you should remember what we talked about when we construct oracles and things like that, that in computing, in assessing the difficulty of the problem, we assume that we can construct our equipment. And then the only thing that we're paying for is the electricity to, or whatever, the amount of, the number of turns of the crank you're going to do to, activate this equipment. In other words, if the equipment that you're asking for is impossible to construct, this is all an academic exercise. The assumption here is that the rules of the game are, you assume that the unitary that's required is doable, and then you ask, how many times do I apply the unitary? Anyway, so the basic setup is going to be is that we have a database from 1 to n of items from 1 to n. I'm going to label them as numbers. And for each of the items in the database is a distinct possibility. In other words, they're not kind of like mostly one or mostly another. They're actually quite separate. You can distinguish them. It's like having a letter A and a letter B, right? We're not worried about somebody writing messily so that A looks like B, saying that, okay, we have a database of distinct possibilities. And the size of the database is capital N. And we're going to use little n's as labels for the possibilities, and little n's inside the vector sign, the quantum state sign, is going to be a distinct state. Okay. Now, one of these is painted phi. We're going to distinguish it by calling it a distinct name phi or n sub phi. And for now, we will assume that it's inside the database somewhere. And as usual, and by now you're experts at this, we're going to prepare a state which is a maximal superposition. In other words, it's the entire database weighed equally superposed. Right? This is impossible classically. It's easy with a bunch of Hadamard gates. We've done this every time we had a quantum algorithm. We had to do this as a first step. And that's basically just signaling that we're going to use quantum parallelism in some way. Okay. So just the usual checks. This initial state S will be, which we're going to call it, it's normalized because of this 1 over n. It is not orthogonal to phi because for now we're assuming that phi is inside the database, but the overlap between phi, which contains the state phi contains the information we need, and state S doesn't. Well, the state S contains a little bit of our information. The goal of the algorithm is to amplify this a little bit. The idea is that we're going to describe an operation which, when applied repeatedly to S, it'll move or rotate, as we'll see, S into phi plus a little bit of jump. And so the idea, and we'll say this more precisely, the idea is that after a prescribed number of iterations, we'll be able to query the end result, and with overwhelming probability, we'll see that it's, we'll keep observing phi. And that's a signal to us that, it's a good solution. Okay. Now, here's the algorithm. Okay, very simple. We'll construct two matrices. One of them is identity -2 projector on phi. Okay. And notice that the action is very simple. If U sub phi operates on any state but phi, it just gives it back. If it operates on phi itself, it paints a minus sign on phi. Gives phi back, but with a minus sign. We're going to do the same thing with the state S. There are two states that we already specified, and we're going to construct unitaries corresponding to these two states. And S is slightly different, but it's basically the minus of the same thing for U5. Well, you can see it here. It's all right. You can check that U sub S and U sub phi are unitary. Pop quiz, how would you do that? Now you have choices. Either you want to put this in the chat or unmute yourself and tell me. Actually, you don't have a choice. These will be on the homework. So you can start the homework now by asking yourself, how would you check that? And if you're not sure, if you ask me a question now, I'll basically tell you. Okay. All right, moving right along. But that's what you should be thinking about. Somebody writes a matrix and claims that they're unitary. You should double check for yourself whether they are indeed unitary, and how would you check that? Okay, let's keep going. Any questions? Any takers on how you check that it's unitary? Okay. All right, so the Grover operation is a product of those two matrices in this order. And the entirety of this algorithm is just keep doing this for a certain number of k's, which we will have to estimate. Right, and the claim is that, as I already advertised, doing this through a sequence of states gamma k, you will end up going from S to the very close to the desired state n sub phi. All right, and following the usual sort of a baby step logic of the induction, we're going to take the first step. We're going to apply this combination to the state S, the initial state. And, this is probably the most difficult step for most of us, because if you haven't seen it before, every detail matters here. So I would strongly encourage you to go through these 4 lines by yourself, because in the remainder of the lecture, this calculation will be repeated with slight modifications. And so, bottom line, you want to be absolutely clear how every step of this first instance of this calculation works, so that things get easier later, right? So we take it in strides, in steps. U sub phi is expanded as 1 minus 2 phi. You apply it to S. Identity applied to S is S. Phi dot S is 1 over root n. We already said that. Somewhere here, you can just check that's true, because phi appears inside here. And so if you take a dot product of phi dot S, it's 1 over root n from the normalization, but then in this sum, only one term clicks, okay? So therefore, we get this result after the first step. Second step, we apply U sub S, again, write it out, collect the terms, and the end result of this calculation is, let's see if I can get my laser point out. The end result of this calculation is that, especially when the size of the problem is large, n minus 4 divided by n is very close to 1. So you're basically applying this unitary to 1, but it's mostly an identity. It's giving you back, sorry, you're applying this unitary to S. It's mostly an identity, so it's giving you S back with a slightly diminished coefficient. The thing that we're watching for is how you're moving weight from S, the initial state, to the desired state phi, okay? And, to simplify things, we can assume that n is very large, so we can replace the coefficient here by 1, and the coefficient here is 2 over root n square root of phi. So we can simplify. Now, the basic idea now is iteration. Again, you should be familiar from math that you can convince yourself that if you iterate, if you just repeat this step, you apply gamma to, so you apply G to gamma 1, you'll get this thing with the coefficient here doubled again. And basically the formula is not doubled, added. And the formula is that gamma sub k is square root of S 2k over root n. And again, we're assuming that K is smaller compared to N. Okay. Again, I think it's obvious if you think about the transfer of weight, how the weight is always transferred from the S to phi. You can be very, very careful about this, or you can be more careful about this. You can do a proper induction on this. You can assume that that's the formula. And you can see that if you apply this step to this formula, you'll indeed, increment K to K plus 1. Okay, also goes on the homework. Check. Okay, so now what's the goal here? So let's assume that this is the formula, and we'll rederive this much more carefully and intuitively next. You can see that we're trying to boost the amplitude of this. Now, this formula was derived assuming that K is much, much smaller than N, but it's clear that you can keep this true and take K to be of order squared of N, that's much smaller than N. And then the outcome of this will be that this term will no longer be vanishing in the limit N goes to infinity. This term will be of order this term. And remember, this term is a superposition over the entire space. So this term is noise, right? That has no information. And so what you can see is that after about square root of N rotation applications of this G, you have a state where phi dominates. And by the way, notice that initially we started off with phi being 1 over square root of N, like its amplitude. Let's see, where do I find it? Yeah, so here initially phi was 1 over square root of N. Its weight was 1 over square root of N in S. So, getting this up to 0.5 is pretty good. That doesn't mean that you're gonna get the answer that what the search is every time. You get 50% of the time. That's pretty good, because the other 50% of the time you'll be getting all kinds of random information out. All right, so I think, all right, I already started talking about probabilities. This is the slide about probabilities. How do we think about this from the point of view of quantum mechanics? We take the state, whatever state we get, gamma K. Here I purposely put gamma K sub G so that we are at the optimal, whatever the optimal iteration order is. We measure N, which is, what it means is that if we want to measure N, the probability, this is going back to the first couple of weeks of this class, the probability of measuring N is given by AN squared. So what we really want is a state where this AN squared peaks near the desired N sub phi. And so if all goes well, it's peaked there. And so repeating the experiment a few times, you just see which of the N's recurs. And if it's peaked, the one that you want will recur predominantly, okay? So let's play the devil's advocate, or rather, every time you see that something working, you want to make sure that when it shouldn't work, it doesn't work, okay? So let's see what it means not to work in this context, okay? So what if the state phi is simply not in the database? Okay, so remember the first state of the database was construct this full superposition of the states in the database. So what I'm doing now is I'm backing up here and I'm saying that assume, now let's consider the possibility that this assumption, let's see, I don't like highlighted because it's a mess. Let me just use the pen. So this assumption is wrong. Let's assume that possibility for now, okay? But we're going to follow all the same steps. So there's again a state, which is a superposition of all the states in the database. Then crucially, what you'll find is that if this assumption is wrong, this assumption is wrong. This is just 0. That state is not in the database. Forget about it. Okay. If that assumption is wrong, we can still go through all the steps, right? But if that assumption is wrong, then guess what? This dot product is 0. And so this piece is just missing, okay? If that piece is missing, then this piece is missing. Okay. If that piece is missing, well, okay, let me spare you the mystery. This piece is missing. And so every time you apply this algorithm, you don't go anywhere. You just stay with the initial state, which is a superposition of the states of the database. And so that means that by the time you get back up here, right, to this thinking, this probability distribution will be essentially 1 over n for n in the database. Okay. And so you'll never see the interesting state. You'll just keep getting random, you'll just keep getting new states every time you try to measure it. And that'll be a red flag for you to know that, wait a minute, maybe the state that I'm looking for is actually not in the database. So you can see that the algorithm consistently gives you the null result. Okay, is that clear? All right, that's comforting. Okay, so now I'd like to, so this is essentially, this is all there is to it. Okay. And I think most of us who know, about basic math of two-level systems and qubits should have an inkling that there's a much clearer geometric presentation that can be done. So in the second half of the class, I will rederive it with fewer words and just a few pictures and 2x2 matrices. Okay. It's an interesting question why one should do this. I don't know the answer for sure. I mean, part of it is aesthetics, because I think that being able to summarize math in visual and geometric ways is often helpful. It gives you a different way to also generalize the problem. If there's something else going on in the problem, you might be able to generalize it if you have a simpler picture for it. I don't know. Yeah, maybe I should put that on the homework. Is this helpful to you and why? All right. So I promised you fewer words, so let's move on and more pictures. So at the heart, the Grover search is a simple 2x2 problem, right? And you already know this even before I tell you anything. We've already said that the state that you are dealing with as you keep evolving is a superposition of two states, S and phi, right? That's the way the search was made. We didn't try to come up with a fancier initial state that somehow knew about phi. No, we said that let's take the state that we can make, let's take the state that we're searching for, and we're going to work in this two-dimensional plane, right? These states are not the same, therefore it's if they were the same, then this wouldn't be a plane, this would be just one state, poorly normalized. Now, it's good that they're not the same. They're not collinear, but they're also not orthogonal. We knew this when we computed phi.s. And so unlike common sort of problems that we've tackled with, where we, from the beginning, would define the problem with a nice orthonormal basis, this basis is not orthonormal. That's usually a bad place to start. So one wants to design an orthonormal basis. Never mind extra details here, we'll come back to it. One thing you should just already start thinking is that what is the angle between these two states, phi and s, in this two-dimensional plane? And you can see that we know what that angle is because we know what the dot product is. The cosine of this angle, cosine of alpha naught, is the dot product between phi and s, which is 1 over root n. So the dot product is nearly 0. That means that it's nearly 90 degrees, but not quite. So here's another homework, sort of a check-in. The steps that we did, the first calculation of applying the Grover matrix to an arbitrary state. in this plane is here. Again, those of us who are savvy with 2x2 matrices, which is hopefully all of us, will recognize these equations as matrix vector multiplication. So we start with a vector A, right? AB. And we multiply it by that, by some matrix, and we get that. Now, A and B, again, I already emphasized that A and B are coefficients of these two vectors, which are not orthogonal. They're normalized, but not orthogonal. So this is not a good representation. The problem, we want to find a better orthogonal representation of the problem. Okay. I keep saying this. Well, from the picture here, because we know what this angle is, we know that these things are almost orthogonal. So let's, in addition, let's keep phi, because that's kind of like what we want in the end. And let's define a vector phi perp, which is going to be basically take S and make it orthogonal to phi by subtracting off a bit of phi that's in it. So this is the formula. You should check that. You will check that. And you can see that it's basically S in the large n limit, but not quite. The important equation that you're solving here is that phi perp and phi are exactly orthogonal, not approximately, but exactly. All right. So now we can go back and we can invert this, right? We can invert phi perp equation to get an equation for S in terms of phi and phi perp. And now we're basically done, because now if we go back to the Grover algorithm and get the unitary and expand it out, this is what I did here, right? So now I'm not applying it to any states. I'm just looking at it as a matrix. And the basic idea here is that S and phi are not orthogonal. We're going to substitute S here, and now we have an expression for phi, for G in terms of phi and phi perp, which I represented as a matrix now. Right, so right, it's on the basis of phi and phi perp, which is now legitimate for all the manipulations we've learned about. Okay. Again, thinking back to your linear algebra, the determinant of this matrix is 1, the transpose is itself. It's basically a rotation matrix, not surprisingly, right? And so we're going to parameterize it as a rotation matrix, cosine and sine with a minus sign. And we're just going to read off the parameters of this rotation, the angle of this rotation matrix. There's only one parameter, which is 1 over n. It's how rapidly you rotate. Right. Okay, and that's it, basically. So the initial state, so now, wait, I should have copied this picture. Whoops, overshot. What happened to my nice? Oh, there we go. Okay. So the end result here is that you take the initial state, which is S, and you rotate it by theta r enough number of times that you cover the distance alpha naught, the angular distance alpha naught. Okay. And we're done. Literally done. Because theta naught is, as I said, arc cosine S dot phi. It's basically pi over 2. And so the number of rotations we need is theta naught divided by theta r. You can see that in the limits n goes to infinity, theta r becomes very close to 0, right? Because n minus 2 over n is practically 1. And you can see that, you know, theta r is basically 1 over square root of n, or 2 over square root of n. And so the end result of this is we've computed the coefficient, right? So remember previously we kind of like guessed that the right number of case steps to take is of order n. Well, it's pi over 4 in the large n limit. The answer. And we're done. This is all I have on Grover search. Any questions? Yeah.
In the beginning, you mentioned that we set it up so our two bases are S and phi.
Yeah. Do you see my screen?
Yeah.
Okay. So in the beginning, I didn't set them up as bases. I just said that there are two states, right? So they're not orthogonal.
Okay.
Go ahead. I'm not sure if you finished that answer, asking.
Well, like, well, how do you know if they are not orthogonal? And like, what if?
Yeah. So no, that's a crucial step. Sorry, you should have asked that earlier if that wasn't clear. This is slide 1. This is basically just setting up the notation, if you like, right? Think of it as essentially writing classical information in a quantum space, Hilbert space, right? So we have a database which has capital N entries. So the size of our Hilbert space is going to be capital N, okay? The orthogonal bases of that Hilbert space are going to be vectors assigned to each entry of the database. So if the database is just a bunch of numbers from 1 to capital N, then each of the states is labeled as 1, 2, 3 up until capital N as orthogonal n's, okay? So N, right, so let me just write it here. So M, oh, come on, don't do this again. Sorry, PowerPoint is trying to predict what it is that I'm trying to do. Okay. So M dot N, these guys are orthogonal. That's how we set it up, okay? Now, one of these guys is special. We're going to keep it. The initial state that we'll create is the superposition of the entire Hilbert space, okay? And that's not really orthogonal to most states, right? Because it's got everything in it. We have to work really hard to create a state that's orthogonal to this state, okay? So, I mean, oddly, this creating a state that's orthogonal to this state is doing a quantum Fourier transform, which you may not realize that, but it's related to that. But here, the most important thing is, this state is normalized. You can check that by essentially applying this relationship and just going to town, so S dot S. I'm not sure if that's the question that you want to know, but I think doing this is a good warm-up, right? So whenever you have each of these is a sum. So the first step in the calculation is a double sum, but then because this is a delta function, in other words, it's only 1 when the two states are the same, then this becomes sort of 1, and this sum upon 1 is n, and 1 over n gives you 1, okay? You can now do the same calculation for phi dot s, and you'll find that this is 1 over root n, and there's only this is 1 only once, and so this is going to be 1 over root n. Am I answering your question, Dustin?
Yeah.
Okay. I'm not. I assume that you were not sure about the orthogonality relationship between phi and s.
Yeah, I didn't get how they were related, but I see now.
Yeah, no. So phi is just one of the entries in the database, and S is the tricky guy. Well, it's not tricky. It's one of the things, right? Coming from the classical world, it's tricky because what does it mean to be superposition of everything in my universe, right? But quantum mechanically, it's allowed, and that's basically the right. And I mean, one of the things is that once you've been doing this repeatedly, it becomes kind of like, okay, you get used to it. It is quite weird, right? So if you think of it's just you just have to accept it mathematically in some sense. But it is part of the quantum theory, the existence of such states, these kinds of superposition states. All right, I mean, good. Is there anything else? So yeah, I mean, this is perhaps the crucial. I mean, look, there are a lot of interrelated statements here, right? This is perhaps the most unusual, the most crucial sort of a moving part in making everything work, right? Okay, this is trivial. Well, okay, I don't want to say trivial because, again, but if you look, I would say this is the most important slide. It's the first time you do this calculation, you realize that there is this transfer. You can see that you start with a state that has a little bit of phi in it, as we discussed. And what you've done is you've increased the amount of phi in it by applying this G. And so the idea is that you're essentially transferring weight from the mess that S is. S is basically the entire database, right? With no information about what's more important, what's less important. It's like the most democratic, the least sort of a, preferential or anything, representation. And what you're doing is that you've cooked this thing up to transfer weight from the flat distribution, if you like, to a distribution that's starting to peak right near the one you want. So I would just walk through this at your own pace. Make sure that every step makes sense, right? Because everything else is basically just putting the dressing onto this result. Here you go, imagine doing it n steps or k steps. Here, well, again, it's a very, because it's a 2x2 problem, there is really no math, there's no new mathematics here. It's just, taking a problem you're interested in and representing it this way. So it's not deceptively simple. It's very simple. Now, the amusing thing, which I don't know if I commented on this during last Friday's lecture, is that this algorithm was invented before Shor's algorithm. And it's a little bit to, especially to people of my generation who were just in grad school, not in grad school, no. So for Shor's algorithm, I was already an undergrad, I think, when that came about, but I didn't know about it, obviously. But anyway, all of this happened before my time, so to say. It's a little bit of a mystery why Shor's algorithm was such an influential, powerful thing, whilst Grover's search algorithm was kind of like, well, it was known, it was kind of understood, but people haven't thought of using it. It's actually quite different now. There are lots of small quantum machines that use Grover search just as a way to speed things up. So I believe the answer for why Shor's algorithm is so much more influential is because it took an exponentially difficult problem, problem that we believe to be exponentially difficult, and solved it in polynomial time. So it's much more of a speed up. But also, and very importantly, it solved the problem which is of current technological use, encryption. And again, so at the time Shor's algorithm was invented and made a lot of splashing, people were already using RSA encryption, but Google was still in its infancy, if at all. And so the notion of searching as a dominant form of sort of technological sort of discourse, if you like, was not in the collective consciousness. So I have a feeling that if Grover search had been invented a bit later than it was, it would have actually made it would have actually been much more topical and influential. But in any case, we have it. We use it now. It's just the way it shows up in textbooks. It's a bit funny that, oh, you know, here's this little cute thing, and here's this amazing Shor's algorithm. I mean, I like both. I've written papers only on Grover search. I've written a paper on Grover search, which is basically trying to make it more robust. All right, so let's see if there are any more questions. I wasn't expecting to go this fast. I mean, I knew this was easy, but I didn't realize, I didn't practice the lecture. Sometimes I do, but not this time. So I didn't anticipate having extra time. So we can use this extra time if you guys have questions. If you want to talk about the homework. People are steadily submitting, actually. There'll be a new homework very soon today. All right, if there are no more questions, I'm sure we can find things to do. Oh, I see. Winston, do you have time to talk? Because we were going to do advising and other things, I think, at some point. Maybe we did, I forget. In any case, Winston, if you want to talk, feel free to stay behind. I'm gonna stop the recording now.